So I'm going to be telling you a beginner's guide to MCMC. So there'll be a little bit of overlap with some of the things Jesse has talked about earlier on, and some of you who've used your own MCMC before, maybe you might know some of these bits, but hopefully we can sort of bring everyone up to the same level at the end of this talk. And then the next talk I'll talk more about priors, so it'll be a bit more in depth in the second one. I should say I'm going to sort of approach this from a fairly practical approach. So thinking like what are the actual things doing, the different components in MCMC, how do you actually get it to work? And I'm also have to declare that I don't actually use MCMC very, very much myself. So I use something else called nested sampling much more than I use MCMC, and I'm happy to talk to some of you guys. I'm here till Thursday, so I'm happy to talk to some of you guys about why I like that versus MCMC, but I'll try and describe as best I can why MCMC is also an excellent tool. Okay, so I first of all want to give a shout out to the Sagan workshop. So I was a Sagan fellow, and my first workshop I ever went to was a Sagan workshop in 2009. So maybe some of you here, this is your first workshop, it was mine. And I'm over here. And this was a great class, and I just want to say I've always really enjoyed the Sagan workshops. I've always got to know people much better than the AAS conference, and I've got to actually meet people here and talk to people here and build collaborations here. So I just want to say what a great program the Sagan is. So my advice for getting the most out of a Sagan workshop is, first of all, it's terrible photos, but I found these online from the 2009 workshop. First of all, attend the talks. Of course, listen to the talks, have coffee with all the Saganites, and this is sort of my story of my workshop, and then give a pop. That's me giving a pop in 2009, or give a poster. Have lunch with all the Saganites, make sure you make the opportunity to actually talk to the people here, and do the hands-on thingies, which hopefully you're all signing up for. This was me with Chaz back in 2009, talking about an exoplanet mission. So my final advice is also bring more than one t-shirt, as you can see I'm always wearing the same t-shirt for the whole week. I've learned that lesson this time, fortunately. Okay, so I'm going to start off with just talking about some things, sort of my approach and what I've learned about statistics and how I approach statistics. So I guess like Eric said, I didn't take a statistics class at university, at college. I sort of learned it on the job. And I think that's true of a lot of astronomers, actually, apart from, I guess, Jesse, who actually really is a proper statistician. A lot of us kind of just learn it as we go. I want to say that for many people, learning from a textbook's great, and it works really, really well. But for me, I'm not that sort of person. I prefer to get my hands dirty. So I don't want to tell you don't use a textbook, but I think if you prefer to actually just start coding and having a go, it's one of the best ways to learn as well. That's certainly how I learned. So I think sometimes statistics can feel a little bit intimidating as a field when you have this huge pile of textbooks. These are actually all books about Abraham Lincoln for some reason, but I can't believe there's so many books about that. But I'm sure there's as many books about, how to code in R with statistics and how to do astrostatistics as there are as this. So don't be intimidated by that. Second of all, the community now, and I think this meeting's evidence of that, is getting really good. When I was first learning, there really wasn't access to these sorts of workshops, these sort of developmental opportunities to learn how to hack, how to code with people, what a posterior is, what is Bayesian inference, all that stuff. And really, I learned by reading different papers. But I think now there is a growing community available to you, and that's something which you should take advantage of. I do want to point this out because credibility, of course I'm a complete fan of Bayesian statistics, but there are astronomers who really don't like it. And as colloquium chair at Columbia last year, I noticed this for the first time, I go out for dinners with all the colloquium speakers, and some of them, I won't say who, they just do not believe in Bayesian statistics at all, like very respectable professors we've all heard of working exoplanets who just think it's complete bogus. And that's really surprising to me, but you should be aware of that it's not, under 35, as I think Eric said, like everyone kind of gets it, but there is definitely an older generation which have a bit of resistance to it, so maybe just be prepared of that, like going in, you're going to have those conversations at some point. So why do this? Why care about statistics? Well, we've already had like a great presentation from Eric about why you should do that, but I think statistics is a means to an end. That's how I use it. I don't necessarily, I'm not a statistician, so I'm not doing it to become a pure statistician. It's a tool as a way to answer questions. But you might find out, as I have sometimes done, that as you do that, you become so interested in the technique itself that you end up sort of writing little side papers and little projects just on the technique because it so encaptures you. And finally, I bet you are all more knowledgeable about statistics than I was in that 2009 workshop. I think I need pretty much zero statistics at that workshop. So you're already way ahead of me. So it really isn't that hard a struggle. It's like that was only 7 years ago, and now I'm speaking to you about statistics. So I sometimes feel a bit of an imposter that I'm here telling you guys about it when I really knew nothing in 2009. But just to prove the point that it's actually quite accessible, you guys can do it, and you are definitely already ahead of me when I was in that point. Okay, so let's get into the MCMC. So what is MCMC, Markov chain Monte Carlo? This is kind of what we're doing. We have some data. Maybe it's a transit light curve in this case. That's kind of the examples I'll keep referring to in RVs. We put it through an MCMC, and we get an output. And it's really important, first of all, just to clarify, the output is not a best fit. It's not the best fitting light curve, the maximum likelihood light curve. You kind of get that as a byproduct, or at least a fairly decent approximation to it, but it's not really the raison d'etre of it. It's not the point of it. It's really designed to give you posteriors. So it's really designed to give you something like this. This is a little mini triangle plot of a posterior distribution. So, and what I mean, also I should say, when I say posteriors, I really mean a set of samples of posteriors. You just get like kind of normally with MCMC you get like a huge ASCII text file maybe, just full of samples drawn from the posteriors. That's really the product that you get, the output you get from an MCMC. Okay, so we've already had a really good definition of what a posterior was from Jesse. I wasn't sure if that was going to be covered, but I'll give my much shorter version. When people say posterior, I guess they're really talking about joint a posteriori probability distribution. It's a bit of a mouthful. It's joint because you have multiple parameters. Usually you're fitting a multidimensional problem. There's not just one parameter you care about. So for example, with transits, you might care about the size of the planet, the impact parameter of the planet, the same major axis of the planet, the orbital period. So all these things form a vector of parameters, a vector which we might use the symbol theta commonly to depict it with. So those are your parameters of interest that you're trying to infer. And you are trying to measure that distribution of those parameters conditioned upon or given some data, some observational constraints, some measurements. So that could be a light curve, it could be a set of RV points, it could be an image if you're doing direct imaging, it could be anything. It's just some observations. And importantly, you're also conditioning it upon a model or a hypothesis, M. So that often gets ignored, but you do have to choose a model. You can't fit data without a model. And I guess there are some non-parametric approaches, but normally when you're doing MCMC, you are fitting a model described by some parameters theta to some data. So your model might be like the Mandel-Aegel code for a transit, or it might be a Keplerian orbit for a radial velocity curve. And sometimes you might add little extra finesses to that. So in my case, I often add a moon into the Mandel-Aegel code as well. So I'm fitting for multiple extra things. But I do have to define what my model is. And that kind of leads also into the idea of model selection later on. So if my very short way of describing what a posterior might be, in a very practical sense, it's when you write a paper and you want to say the radius of the planet is 1 Earth radius plus or minus 0.1 Earth radius. It's basically that number. That's why you're doing that's why you're trying to infer the posterior distribution. So kind of the point of it is that you're trying to get a credible interval for the parameters of interest. Now it's not quite a strictly correct definition, but in a very simplistic sense, that's probably the thing you most care about for the purposes of your paper that you're writing, is to be able to say the size of the planet or the mass of the planet equals x plus or minus y. So just as a very simple way of thinking about why you are doing this, that's probably why you might care about doing a posterior distribution. I also like to think of it like this way. Posterior, I mean, this is very obvious, but posterior is what you think the parameters are post having your data. That's why it's called a posterior. And your priors are what you think the parameters are prior to having your data. So that word's not just like fictional, actually has a purpose here. It's really trying to remind you of the process of taking in data and what it does to the parameters. So it's this, it's going from a prior belief, we're applying some data, conditioning upon some data, and getting a posterior belief. So this is like a typical example of what a posterior might look like. This is from one of my papers. This is a 16-dimensional vector for theta. I think this was for a 3-planet system that we were fitting. So you have many, many parameters. The more parameters you have in your MCMC, generally the longer it's going to take. Something like 16 isn't that bad, actually, but once you start getting into hundreds, you really need to think very carefully about the algorithm you're using. Otherwise, you're going to be waiting an infinite time for your MCMC to converge. So these are sorts of a typical way we present posterior distributions. This is a triangle plot, sometimes called a corner plot. I generated this with Dan Fulmer-Mackey's code called Corner. I really recommend it. It's a nice little Python routine. It's pretty simple, but it'll just spit these out for you. And it often can put like the plus or minus numbers up here as well if you want it to. And it can sometimes draw grid lines for you and show you where the best fits are and stuff like this. So this is a really nice, simple way of just generating your posteriors. It's very common to see figures like this in papers. And really what you're looking at is at the top here, you have a histogram of the marginalized posterior, just for that one parameter choice. And each, so this might be, say, radius of the planet. I can't quite read what it says. And this might be, say, impact parameter. And then this is basically the covariance almost between these two. So it's the joint posterior between those two. So you can see if there's correlations between your parameters. So for example, these sorts of parameters are very nice. When you see these, you're very happy. There's no correlations. Your MCMC will love those. It will work very efficiently. Whenever you have things like a little bit like this, or this case in particular, where you have strong covariance, your MCMC is going to sort of struggle with those a little bit unless you're using a more sophisticated MCMC algorithm. And I'll talk about that a little bit later on. Okay, so just to re-emphasize, I think there are dashed lines on this. I can see it on mine, but you can't see it on here. That there are, usually you would put dashed lines on here to show sort of, typically what we quote is the 68.3% confidence interval. Some people use 2 sigma instead of 1 sigma. But that's primarily the output that you would put in your abstract. You wouldn't obviously put this in your abstract, you'd put that number. Okay, so what are we doing? I've lost some symbols here. We're going from a prior belief to a posterior belief. Let's see if these come back. We don't have them. So I guess I can remember what these are. So this is P of theta. There should be a theta in here, given some data, D, and given a model, M. So maybe I can put that on the blackboard somewhere so we have it down. Can I can probably reach up here. So it's P of theta, given some data, and a model. So that's the posterior we're trying to measure. Sorry that the slides aren't showing all the symbols. I hope this isn't true all the way through. And we're conditioning that on the probability of some data. So now I'm going to put the D in there, given theta and given M. So this is called the likelihood function, this thing here, when it has the symbols in it. And this is my prior in blue. So this is P of theta given the model M. And down here, you basically have a normalization constant. If you follow online, the slides I think they're on the website. If you have your laptops open, you might be able to actually see these symbols, hopefully. I've also put them on the GitHub, David Kipping / Sagan 2016. They're PDFs, so they should definitely work if you want to follow along on there as well. So, sorry the symbols aren't coming up here, but you can definitely catch them on the GitHub. That's David Kipping / Sagan 2016. You'll be able to find the PDFs on there. This is the first talk, mcmc.pdf. Okay, I'll continue anyway. So we've got likelihood times by prior divided by the evidence. And really what we've just used here is Bayes' theorem to flip these things around. The evidence, in fact, I might be able to put, this isn't my machine. Okay. I can't do that. The evidence is the marginal likelihood, which means that it's an integral of the likelihood over the prior. So we've basically put some integration symbols in front of this and done d theta on the end here. So it's just a very big, horrible integral. Because it's marginalizing out all of theta, the parameters of interest, it doesn't depend on theta. The actual final product, it isn't a function of theta. You've marginalized out theta. So because of that, it doesn't change. In an MCMC, what you normally do is change the theta and see how good a fit you're getting. But this thing doesn't ever change because it doesn't depend on theta. So normally MCMCers don't care about that term, and we completely ignore it. And I'll be able to prove that to you explicitly later on. So this is the normalization factor. It's P of theta, P of d, PD given m, is the integral of P of theta given d times by P of theta given m. So the prior multiplied by the likelihood. Okay, there we go. This is what it should look like. It's actually already still screwed things up a bit, but we're more or less there. At least we have the symbols. So P of d is the likelihood here, given theta and m. And now you can see what this integral fully looks like. Okay, so in MCMC, we're really just trying to get the posterior. So this becomes a proportion. Oh, this becomes a proportionality at the top here. We just get rid of that evidence term. And a common sin, I think, by maybe not all MCMCers, but there's definitely some papers I see where this happens, is to sort of neglect the prior, not think too hard about what my priors are, and somehow it doesn't matter. And that means actually you're implicitly making certain choices. So we'll come back to that in the next lecture a little bit more. But I just want to emphasize that it's a pretty important component to this equation. Okay, so let's expand this out. This should be sort of my toy box of what this is doing on the inside here, the MCMC. So you have a sampler, which is basically the way that MCMC is going to explore parameter space, how it's going to move around for different parameters. And it is going to basically generate different thetas that it's going to want to try out. So remember, the thetas are the sets of parameters, like the size of the planet, the mass of the planet, things like that. It's going to generate essentially random guesses, let's call them, and then it's going to spit that out to maybe a module that is going to tell you what the prior probability of those thetas are, and that's the prior probability it returns back. It's going to spit out a theta to a model, and the model with the data is going to tell you the likelihood of that particular choice of parameters. And then it's going to take likelihood times by the prior to evaluate the posterior probability of that particular choice. And then you're going to make lots and lots and lots of jumps and evaluate the posterior probability all over, and we'll get to exactly how that works. But this is kind of a rough schematic as to if you were writing a code and you wanted to have a few functions, this would be the functions you'd have. So you'd have a sampler, you'd have a model, and you might have a function for your priors. Okay, so actually the point of the sampler is not just to make random guesses, but to make sort of intelligent guesses. You can just, of course, if you wanted to make completely random guesses, it's a pretty inefficient algorithm. So these are sort of the ingredients you need. You need some data and a model, and I'm just going to sort of leave that to you. I'm not going to talk about that in this talk. Hopefully you have some data, and hopefully you know what your model is. In the case of transits, like I said, you could probably just use the Mandel-Lagor. If you're using RVs, it's probably just a Keplerian. And then if you might be doing something fancier, but hopefully you know what your model is. Then you're going to have a sampler, an equation for what your likelihood is, and an equation for your priors. I say equation, it's really a function, but we can also call it an equation. So let's focus on the likelihood. I'll go through this quickly because Jesse also talked about the likelihood function, how to write down a likelihood. But essentially you have a set of observations that are perturbed by some stochastic noise. So the observations you get are not equal to the truth. So for example, if I'm measuring a transit, I don't actually measure the true brightness of the star. I'm measuring the true brightness of the star plus some stochastic noise element on top of it. And when you're writing down a likelihood, you're trying to guess at what that epsilon term is doing, what that noise term looks like. In the vast majority of astronomy applications, I'd say, certainly in exoplanets, people tend to use a Gaussian likelihood function. So this assumes that every single point is independent of every other point. There's no correlated noise structure, for example, in the data. But it's attractive because of the central limit theorem, that a lot of distributions do tend toward a Gaussian. I mean, in principle, really for photometry, you should be using a Poisson distribution, but people normally use the Gaussian. So what we're looking at here, it's just the PDF of a normal distribution. That's all I've written down here. So you can write down the likelihood for any distribution you want. It's just the PDF, the probability density function, which is like the standard analytic equation describing that distribution. So in this case, I'm defining R here as the residuals between my model and my data. So I have some data, and I've given a particular choice of theta, and it's predicted what the transit looks like, and then I take the difference between them, and that's my residuals. So if it's a really good fit, those residuals should be pretty flat. And that's what that vector R describes. So that's Ri, so that's the ith element of R. And then each of those points has a measurement uncertainty, sigma. In this case, we're assuming, remember, that's just like a normal white noise distribution. There's no correlations. And then we just take the product of this. So this is the likelihood function. But normally, we tend to write it as a log likelihood function, just because this can be a very, very large number if you write this down. So this tends to be a much more stable numerically routine to have in your code, given the working precision of your language. So we tend to talk about log likelihood more often. It also has some advantages because this thing here becomes a constant, for example, and if your measurement uncertainties are not being fitted, like you know what your measurement uncertainties are, then that's also a constant. So you can actually just write down the log like is some constant minus half the chi-squared. So this is just the chi-squared here. So it's the sum of the residuals over the measurement uncertainties. So by going to log, of course, you'll notice that I've gone from a product to a sum, just using the law of logs when you do that. Okay. So I'm going to sometimes use the word chi-squared because when I didn't know any statistics, I knew chi-squared. That was like the only thing I knew. So I think that's like a good grounding. Hopefully all of us know what we mean, hopefully, by chi-squared. It's like the least squares estimation of our model. Okay, so you don't always have to use a Gaussian likelihood function. You can also use whatever likelihood function you want. You don't always have to assume each point is independent. You can have correlated noise structure. One of the most popular ways to deal with that right now in exoplanets is with Gaussian processes. It's not the only way, but it's definitely one of the most popular ways at the moment. I don't think we have any talks about it at this workshop, but I recommend having a look at Dan's speaker deck talk here. I certainly learn a lot from Dan's amazing slides he has on speaker deck. He has a whole bunch of great talks on there, and they're really designed that you can just follow along by clicking through, not necessarily having to like hear him speak, but it's great if he's there, of course. But this is a great resource, his repository here. So essentially what you're doing when you do a Gaussian process is you're saying that there's some covariance between my data. So the second point along, the third point along is somehow correlated to that first point. But there's almost a memory in your data, essentially. The third point has some memory of what the first data point did. So if the first data point is high, the second and the third point might be more likely to be high as well, just as a result of that correlation. So you can model that by writing down a huge matrix, and this is basically a matrix where each element is depicted by sort of a color coding scheme. And in a Gaussian process, although you don't know what the covariance matrix is, you can model it. So you can say, I'm assuming it looks like maybe an exponential drop-off from the diagonal. So the diagonal has huge power. Of course, it has to. And then as we go out towards sort of the edges, it can have like an exponential drop-off. So that's called an exponential kernel. I don't want to go too much into that, but just to say there are ways that you can deal with covariance. So the likelihood is very flexible. You can do lots and lots of ways of dealing with your data. So have a look at that talk for more. Okay, so we've got our likelihood. I'm going to talk about priors in the next lecture. So that leaves me free to talk about sampling. So I'm going to mostly focus on the metropolis algorithm, just because it's the first algorithm you should learn, I think, about MCMC. It's probably the simplest. Harkens all the way back to 1953. But there's many, many, many advances of different, more sophisticated MCMCs since that time. But this is basically what a metropolis algorithm does. We define some function. We have to define some function for what our likelihood is, like we just talked about. maybe it's a normal distribution. We have to define some priors, which we'll talk about in the next lecture. And then you're able to now calculate what I'm calling curly P, which is the posterior probability, for any given choice of theta. So it's like a black box. You give it theta, it spits out curly P for you. Once you can do that, you're set up to basically run an MCMC. So let's say that the true answer between two parameters here, this is parameter 1, this is parameter 2, A and B. The true answer is over here, but I don't know that. The true answer, by the way, isn't going to be the very, very highest posterior probability. It should be pretty close to it, but just because of the effect of noise, it's going to be probably slightly off. Actually, if you completely choose the wrong likelihood, it's going to be miles off. So you want to make sure you choose a good likelihood. This point here you can think of as having a high posterior probability, a high P, which means as long as you don't have pathological priors, it should be a high likelihood solution as well. Which, if you don't like thinking of likelihood, you can also think of that as the best chi-squared, the lowest chi-squared point in this map. We start out from, say, some random guess over here. If these were uniform priors, then this is like a box which bounds my parameter exploration space. So I start out from some initial guess. It's probably not going to be a particularly good guess to get started with. So it's probably a low probability density, which means it's low likelihood or high chi-squared. And what we're going to do is make a jump, and we're sort of trying to get towards this region. So it's not like a narrow hill. If it's a very, very sharp hole in the ground, your likelihood function, it's really basically no algorithm will be able to find it. It's almost impossible. It's like trying to find, John Skilling used to tell me, it's like trying to find a pole in the Antarctic, right? It's if you have this vast landscape and you're just trying to find a flagpole planted in some random place in the middle of the entire Antarctic continent, no algorithm's really going to do a very good job at doing that. So you're hoping you have some sort of fairly wide region where your parameter exploration code can get sort of locked into and wander around. So what we do is we try a jump from this initial parameter set, and we are going to accept that jump if the posterior probability is higher. So if P trial is higher, the probability is higher than P0, then we're going to accept that jump. So that's fairly obvious reason to proceed along that route. So we proceed along. But some guesses are not going to be better. We might make a guess which is worse, and in that case we're going to accept the jump with a probability of P trial divided by Pi. So this is actually why the evidence doesn't matter, because let's say I included the evidence terms in there, then remember the evidence terms don't depend on theta, so if I multiplied this by a constant here and a constant here, then the two constants just cancel out. So that's why it doesn't matter, the evidence, when you do an MCMC. You can see that explicitly by the metropolis rule. So we accept this jump with this probability. So obviously if P trial is really, really bad, then this is not going to be accepted to great probability. It's very unlikely we'll proceed along that route. But this gives the algorithm the flexibility to get out of local minima. So we might, if we only accepted steps if they were better, we could get very easily trapped into local minima. So this gives it the chance to go uphill. It gives it the chance to get out of those local minima and find deeper minima elsewhere in the parameter space. So that's actually pretty much it. So we try a jump and then we accept it, reject it based on that rule. You can summarize the rule in this box pretty much. And that's really all there is to it. There's a few complexities that we'll go into, but a very brief summary might be that if you use that when you're actually coding up your algorithm, that would be pretty much the main way that you would be assessing whether you're going to proceed along these steps. That's called the metropolis rule. So you do that over and over again, and you will hopefully perform sort of a quasi-random walk. The algorithm is endless. It's never going to stop. It's never going to reach the minimum and say I'm done. It's just going to, because it can always get out of those minima, remember, it's just going to essentially orbit around the best solution. So it's kind of like a drunkard in the streets. He can smell alcohol, and he just wanders around. He's kind of blind, and he can't quite get to the pub. So he's just drifting around looking for this final best solution. But that's good. That's what we want. We want a long chain of random walks around here. Okay, so this chain is called a Markov chain as well. That's the lingo here. So this point here, we'd normally call this burn-in. So you're not actually interested in this. This is just when it's initially trying to get to that good solution. So we have to reject these steps. If you include these steps in your posterior, well, they're not representative of the target distribution that you're trying to get, basically. So you need to exclude these to have a clean posterior. And we'll talk about how to do that as well in a second. So I just want to point out. Oh, sorry. Yeah. Question.
So the previous slide.
Yeah. Go back.
Isn't it possible to make like progressive step size and then start with large steps, make them finer until eventually you reach a small area?
Yeah, I mean, if
Could you repeat the question, please?
yeah, so could you change the small size? I think what you're suggesting is making the small size smaller and smaller as you get closer and closer towards the solution. So I think in that case, probably the reason for doing that would be that you wanted to get the most precise estimate possible of the maximum posterior probability location or the maximum likelihood location. So that's really a minimization problem rather than a posterior inference problem. So in that case, you would just use like a simplex algorithm or a gradient descent, or there's a whole host of downhill algorithms which will do that for you. But you probably wouldn't use an MCMC if your primary objective was to try and very, very precisely measure the best point. You would just use a completely different class of algorithms, or at least I would, to do that. But in general, yes, there are MCMC samplers which do use adaptive step sizes. The Metropolis normally doesn't. Most implementations don't, but there are, and we'll talk about some towards the end of the lecture, some that do. Or sort of make it a bit more elaborate than just a simple step size every time. Actually, even here, the step size is not fixed. So I haven't talked about the proposal function yet. So if you give me a couple of slides, I'll show you how we generate those proposals. I want to point out that sometimes you see the Metropolis rule written out differently, but I'd say that it's kind of inaccurate. So this is the way I've written it down based on the posterior probabilities. Maybe I've made a simplification here that I missed, but this is definitely a simplification just to frame it purely in terms of likelihood, not in terms of posterior probability distribution. You're ignoring the effect of the priors if you do that. Or essentially, this would be true if you had uniform priors for every single parameter, that it made no damn difference where you were, the prior was the same everywhere. Then it's okay, but technically you're kind of making a shortcut of this fuller expression. And then you might also see it written like this, where you just talk about chi-squareds. And that's someone both ignoring the priors and definitely assuming normal error bars, essentially, on your measurements, a Gaussian likelihood function. So that's explicitly assuming a likelihood function there. Whereas here, it's more general than that. And here, it's even more general than that. So that's just different ways you might see this being written out. But I personally think this is the most general way of writing it out. But these aren't necessarily wrong, but they can be wrong in some cases. So I talked about burn-in. Oh, in 5 minutes already? Okay, I better go quick. We talked about burn-in. How I would get that is just by eye. This is just plotting, let's say, the chi-squared by your step size. You can usually see it pretty easily. I'll also show you a brief trick later, how you might do that automatically. But this pretty much defines your algorithm. You define your likelihood, your prior, and then you make jumps. And you keep doing your jumps over and over and over again until some certain point. Typically, people will say, oh, once I've got like 10 to the 5, 10 to the 6 accepted jumps, then I'll stop. So you just have a very large number of samples. If you only have 100 samples, you should probably run your chain a lot longer than 100 samples. You want like many, many thousands of samples. Some people run like a billion even in some cases, but that's kind of excessive. Okay, so how to make your proposals. I'll be quick on this, but there's many, many ways to make proposals. The simplest thing is just use a normal distribution. So you start out from your trial, and you're starting out from some initial position, and your trial is going to be that plus some normal centered on 0, or I guess really centered on this point, plus some scale, some standard deviation. And you have to choose that. And that's non-trivial to choose that. And when you first write an MCMC, that's like the thing you bang your head against the wall against the most, is tuning these damn jump parameters. And that's why actually I don't even recommend really using Metropolis that much, because this is like a black magic almost. For the person has to spend, it takes a lot of expertise to get those proposal sizes right that you're going to have an efficient MCMC. But in principle you can do it, and for simple problems it's usually okay actually. and you're aiming for a reasonable acceptance rate, something sort of order of 50-40%. You have to do that for every dimension as well. This is, for every dimension you have to choose a jump size parameter. This is why it's tricky for high dimensional problems. So some checks to do. Check your burn-in. One thing you might do is where the chain's likelihood exceeds the median likelihood of the entire chain. You can use that to demark where the burn-in has happened. There's no right answers here. These are just suggestions as things which you could use, which might be practical. You want to check that your chains are well mixed, which really means that they've gone back and forth along that green zone many, many times. They've done lots and lots of traversing's around independently. And for that, we sometimes use something called the effective length. And that's kind of measuring when the chain sort of flips over. So if you plot what the chain's doing as a function of, get this right around. So it's kind of jumping up and down, up and down, up and down. And then once the chain sort of flips over, this is, say, my likelihood, and this is the parameter. Once it flips over, you might call that one effective length. So sometimes you use like the autocorrelation of the chain. When it flips over greater than about 0.5, you might define that as a new effective length. So you want to make sure you have lots and lots of effective lengths. If you use a really, really small jump size, it's going to have like thousands of steps here before it eventually finds sort of a new effective chain. So you want to make sure you have plenty of those. And for convergence, a good thing is just to run the chain multiple times, actually, and just to make sure it's getting to the same spot. Okay, so I'll try very quickly to finish off here and get through the last few bits. Normal proposal functions aren't going to work always. This is a case where a normal proposal is going to really screw you over. You're going to have to use a really small jump size here, right, in order to explore that green zone, because otherwise you're just overshooting. I mean, this is kind of isotropic. You're just going to overshoot your green zone most times, your high likelihood zone. So you'd have to use a really, really small jump size, and then it would take you ages to get all the way up here. It'd be a pretty inefficient process to do that. So metropolis and simple simple proposals can have problems. Another example is a multimodal problem. So I have two good solutions. The MCMC can get out of local minima, but if the minima is deep enough, it'll be stuck there for a very long time. So in principle, you might have to run like billions of chains before it has a chance of getting over here. So that's also bad. So there are issues where this simple approach is not going to work. My advice, though, is to still write your own one. It actually doesn't take much work at all. It's like 5 lines of code. And I find that was the way I learned. It was actually to write my own and experiment with it. I feel like that teaches you a lot. So my advice is to write your own, but don't necessarily use it in actual applications. So maybe like Eric has suggested, there are lots and lots of much smarter packages than you could ever write, to be honest. So you may as well just use one of those. But this gives you the grounding that you at least have a familiarity as what these algorithms are actually attempting to do. So I'm just going to quickly run through a few of them. Some examples, there are hundreds, to be honest. So just a few popular ones. The first advancement you might do is go from metropolis to metropolis-hastings. Metropolis-hastings allows for asymmetric jumps. So before we were doing a normal distribution proposal, so it went everywhere isotropically. But I might prefer to go in the positive direction than the negative direction. That's an asymmetric proposal function. If you do that, you have to modify your acceptance probability by basically the ratio of going from A to B versus B to A, the ratio of that probability density. So that was something that was written about back in the 70s. So one of the most popular algorithms, metropolis-hastings. Most of the time people say they're using metropolis-hastings, they're actually just doing metropolis. But I guess it's kind of the same thing. Okay, I've run out of time, so I'll go very quickly. You might do simulated annealing. Simulated annealing is when you essentially change the acceptance probability to have to the power of 1 over a temperature. And the higher I make the temperature, the more likely it is to make the acceptance. So you start out with a very, very high temperature, and what that basically means is it's pretty much going to accept everything. Every proposal it's pretty much going to accept if you make the temperature high enough. And then you slowly cool down the temperature. So you let this thing get sort of into an equilibrium almost in your parameter space, and you slowly cool the temperature down, and your chain will settle down, and it should find all of those local minima as it goes. So it's a way of sort of catching all those multimodal problems. Parallel tempering kind of does the same thing, except rather than cooling the temperature down in serial, it does it in parallel. So we actually have multiple chains running at different temperatures, and they can speak to each other. So the top temperature chain, which is going all over the place, might say, hey, I found a really good solution over here, and it feeds it down to the next chain, and then if it thinks it's a better solution than this chain, it will feed down. So eventually the best solution can sort of propagate down to the lowest chain. The important thing is that in both simulated annealing and parallel tempering, your posterior can only come from the lowest temperature, basically the T1 chain. You shouldn't use the higher chains for your posteriors. So it's kind of wasteful in a way because you actually throw out all this information. You can use it to calculate the evidence, which is nice. So it does actually give you some advantages. And then finally, we have a couple of very similar algorithms. Affine-invariant is very popular these days because of Dan Fulmer-Mackey's code MC. Essentially, you have like a set of walkers like this. They're each independently exploring parameter space, and we choose a particular trial that we're going to, a point that we're going to trial off. We choose a test point, which is a different walker, and that becomes a vector displacement position. And then we're going to move along that vector along some scale. So that's a much smarter proposal, because now instead of moving in any direction, it's always essentially going to move along this covariance function. So it's going to be much more efficient to do that. It's also far fewer free parameters. You only have to choose basically the scale size at which you're doing these jumps. So that's extremely popular. MC, it's in Python. I'm sure many of you might already be using that. A slight tweak on that is differential evolution, when you have, you basically have 3 points now rather than 2 points defining your proposals. You have a test point here, a test point here, and you displace that vector. So I displace that vector onto this one, and then again do a scale along it. So ExoFast does that, I believe, Jason Eastman's code. And I think MC now does it. Dan told me in an email last week that he's either writing that now or it's a new feature, so I think that's now included. So I'm going to leave that up and take questions. So sorry I've gone a little bit over, but yeah, hopefully got a few questions.
Always sort of struggled with.
Is there a particular example there that you were thinking about? Like with the MC package, for example, it's doing the affine-invariants.
That's the one I'm used to. So right, the affine-invariant.
Well, I think there are some rules of thumb. My student, actually, Emily Sanford, uses MC a lot, and I understand that in the README file, Dan has some recommendations of how you should choose those parameters. So, for example, I think the number of walkers you want to choose should be several times the dimensionality of your problem. So if you have 6 parameters, you should be using like 20 walkers in order to efficiently explore parameter space. In terms of how long to run it, I don't know in MC's case, but I think a general rule of thumb is to inspect your chains, run it for a certain amount of time, see how it's doing, have a look at the chains. If they look like they've converged and you have enough samples, then that's fine. But the best way is to do a fairly short run, see how it's doing, and then extend if necessary, would be my advice. Nested sampling? Yeah, I guess I would summarize nested sampling how it's different from this. Is MCMC is almost like inside out. It starts from a point and it walks along parameter space trying to get all around. Nested sampling starts from the outside in. So it generates a very large number of points over the entire box, and it tries to create a contour of, say, constant chi-squared, you can think of it, or constant likelihood, and then it tries to shrink that net down as it goes and sort of pinch onto each mode as it goes. So that's like the simplest explanation to describe, but really the only reason to use nested sampling is if you want to calculate the evidence. If you don't want the evidence, you should just use MCMC, to be honest. If you want the evidence, though, this is not going to do it for you, and that I usually do in the work I do. So. Garbage in, garbage out.
One last question? All right, if not,
Okay.
thank David. We'll hear from him again soon.